All right, welcome. Today, we're going to get down to the absolute basics. We're looking at the huge divide that splits the building blocks of our entire world into two very different families. You've got your metals and you've got your non-metals. So let's jump right in.
Seriously, think about it for a second. One is this shiny, precious, valuable ring. The other is a dull, black lump of carbon. They couldn't be more different, right? Well, they are, and our mission today is to figure out what really makes them tick.
So, where do we even begin? Well, let's start by being detectives. We're going to look for the most obvious clues first, the physical properties. I'm talking about the stuff you can see, touch, and feel. The things that practically scream, hey, I'm a metal.
Okay, first up, and probably the most obvious thing, is that shine. When metals are pure and clean, they have this brilliant, reflective surface. That's what scientists call metallic luster, and it's our clue number one for sure.
Next, we've got a genuine metallic superpower, malleability. This is the incredible ability to be hammered, squashed, or pressed into super thin sheets without shattering. It's the reason we have aluminum foil and why we can shape metal into cars. Just try doing that with, I don't know, a chunk of sulfur. It's not going to happen.
And if you want to see just how wild this gets, just look at gold. It is the most malleable metal we know of. You can take just 1 single gram of it, that's lighter than a paperclip, and flatten it out into a sheet that covers a whole square meter. Absolutely mind-blowing, right?
Okay, so malleability has a twin sister, and her name is ductility. Instead of hammering something flat, this is the ability to pull and stretch a metal into a long, thin wire. This is why we have copper wires powering pretty much everything in our homes.
And this is where it gets just unreal. That same tiny 1 gram piece of gold, you can stretch it into a wire that's 2 kilometers long. Think about that. That's, what, like 20 football fields? All from a tiny speck of gold. It's amazing.
And yeah, of course, there are the other classic metal traits we all know. Metals are usually pretty hard. They're fantastic at conducting heat and electricity. It's why your cooking pot is metal, but the handle is, plastic or wood. And they're sonorous, which is just a fancy way of saying they make that nice ringing sound, like a bell.
So there you have it. Case closed. Simple, right? If it's shiny, bendy, hard and solid, and it conducts electricity, it's a metal. If not, it's a non-metal. But what if it's not that simple? Because this is where things start to get a little weird. It turns out the world of elements is filled with rebels and imposters. I'm talking about the rule breakers that just love to mess with our nice, tidy little boxes. Yeah, it turns out for pretty much every rule we just set up, there's an exception. We think metals are solid? Bam! Mercury is a liquid. We think they're super hard? Well, you can slice through sodium with a regular dinner knife.
Oh, and it doesn't stop there, not by a long shot. You've got metals like gallium and cesium that will literally melt in the palm of your hand. And on the flip side, there's iodine, a non-metal that has that classic, shiny metallic look. And don't even get me started on carbon. It's a non-metal that gives us diamond, the hardest thing out there, and graphite, which conducts electricity. What is going on?
Okay, so if we can't trust our own eyes, if physical properties are totally misleading, what's the real difference? How do we actually tell these elements apart? Well, the secret isn't in how they look, it's in how they act.
And that, my friends, brings us to the real heart of it all. Chemistry. You find out an element's true identity by seeing how it reacts with other stuff. This is where we draw the real line in the sand.
You want to know the single biggest test? It's how they play with oxygen. When most metals react with oxygen, like when iron rusts, they form what are called basic oxides, which are basically the chemical opposites of acids. But when nonmetals react with oxygen, they almost always form acidic oxides. That is the real dividing line.
And check this out, because it shows another key thing. Even inside the metal club, not everyone behaves the same way. Just look at how they react to water. Some, like potassium, hit cold water and just burst into flames. Others, like iron, need it to be super hot steam to do anything. And then you've got the cool kids in the back, gold and silver, who just don't react at all.
So, wow, that's a lot of chaos, right? Violent reactions, calm reactions, no reactions. So how in the world do we make sense of all this? Is there some kind of ranking system? Well, you bet there is.
And that brings us to the ultimate guide for how metals behave. It's a system that chemists use to figure out who's who in the zoo, and it creates a crystal clear pecking order for all the metals.
Let me introduce you to the reactivity series. This list right here is the key to understanding pretty much everything about how metals will act.
So here it is, the whole shebang. Think of it like a league table. At the top, you've got the most reactive players, the ones that go crazy, like potassium. As you go down the list, they get less and less reactive, all the way to the bottom where you find gold, which hardly reacts with anything. Simple as that.
Okay, cool list. But what's it for? Well, you can predict what's going to happen when you mix them. It's like a game of chemical king of the hill. A metal higher up on the list can literally just walk up and kick a metal below it out of its spot in a chemical compound.
Okay, but that just leads to the biggest question of all, doesn't it? We know what happens, but why? Why are some elements so desperate to react and cause a scene, while others just don't care?
And the answer, the deep, fundamental reason for all of this, comes down to one thing: electrons. See, atoms just want to be stable and happy. And for an atom, happy means having a full outer shell of electrons. The superreactive metals have one or two extra electrons they are just dying to give away. Nonmetals are usually a few short, so they're desperate to grab them. And that dance, that constant giving and taking of electrons, that right there is chemistry.
So let's end on this little thought. The most reactive metals, the ones that cause all the fireworks and explosions, they're just the ones that are the most willing to give something away to find a little peace and stability. Kind of makes you think, doesn't it? What does that really say about generosity? Something to chew on. Thanks for joining us.